Hello everyone, welcome to part 2 of the third lecture. In this part, we're going to talk about first start with the exponential functions. So what is an exponential function? So remember previously we talked about exponential growth, which is a function that grows at a very fast rate. So you can say, let me change color and replace this. So we can say f of x equals to b of x. Now b itself, so this one is called the base. It is a constant. You can say it can be a number of 2, a number of 10, etc. So this is the base that does not change. What's changing is the variable here. So variable x is located at the exponent of this function. So it's called an exponential function. So x will change from 1 to 10 to 100. So this is called an exponential function. If we graph it on the coordinate system, so it can be something like this. Right, growing very fast, and as we move towards the right, then the rate is even bigger in terms of the speed of increase. So this is one example of exponential function, and also it can be something like this. Can be something like this. Let me draw. Right, so this could be 2 to the power of x, and then this could be the 0.5x. This is one way to write it. So as you can see, that if b is bigger than 1, right? So 1 itself is actually sort of separating the line here. So the underlying condition is that b cannot be 1, and also b is positive constant. So b should be positive, and also b is not 1. So if b is 1, then no matter how x changes, it always be 1, right? So there's only 2 cases, and b bigger than or b equal to 1. Less than 1. So if b is bigger than 1, that would be this the case. This case. So the line is actually increasing. So it's an increasing function. So if b is less than 1, which is take this for example, then the function is actually decreasing. So that's something to keep in mind. And a few other things. So remember there's this point here where all the exponential functions passes through. And this point is very particular because if, say, x is equal to 0, right, then all the any exponential function will always be 1, right? Because that's how it calculates the coordinates 0 or 1. So this is particular point where the exponential function will always pass through. The other thing is that, for example, for increasing function, if x goes to the left, goes to negative infinity, then this line will approach the horizontal asymptote, which is x equals to 0. Right, so this x0 is the horizontal asymptote, which is also the asymptote for the second case. So if so in this case, if x goes to infinity, then this line will approach the x-axis, which is x equals to 0. Sorry, my apologies. So it should be y equals to 0. As the horizontal asymptote. So this is by design the case where x goes to infinity, then y itself will approach some value. So in this case, y is equal to 0. So these are just some high-level characteristics of the exponential function. And let's dive into look at some properties of exponential functions. So first property is that say we take a number a, and a is a constant, and we know that a cannot be 1, and a should be positive. So we can take a equals to 2, for example, and we have the variable, which I just write as var x and y, so they are changing. So first property is ax to the power of x and ay. So if we have a expression like this, then we can simplify as this, so x plus y. So in the case, if these two multiply together, then we can actually add the exponent together. And similarly, ax divided by a to the power of y can be expressed like this. Right, so we're sort of converting the multiplication to a plus, to an addition operation. And this is similarly division converted to a minus. Also, we have a to the power of x and to the power of y can be expressed like this. So we basically multiply x and y. And similarly, we have a, b, and b is also another constant. If we raise that to the power of x, then you can distribute x to each item inside the parentheses, bx, right? And this works the same for the division of a over b, and we can distribute x to each term inside. Right, so this is how we can manipulate the expressions. So this is just a high-level loss for the exponent. And secondly, we have so if we have a to the power of x and a to the power of y equal to each other, so this happens if and only if, so I should find for f, x is equal to y. So this happens only if x and is equal to y. So that's another rule to keep in mind. And the rule is that so if x is not equal to 0, then we have a to the power of x, b to the power of x. This stands if and only if a is equal to b, right? So this is also intuitive to understand. So the base has to be equal for these two exponential functions to equal to each other. So that's just some high-level properties. Next, we'll look at the example in the case of compound interest. So this actually very much related to our real life. So say we have the principal denoted as P, for example, it could be $100 I save it in the bank. And then the bank gives me an interest rate, which is usually the annual interest rate, for example, 5%. And I can say, just write the example here, 5%, and then I can save it for example, 1 year. So T usually stands for how many years we put in the bank. So in this case, I want to calculate what is the future value after 1 year. So what is the principal plus my interest? So I can calculate, like, for example, principal times 1 plus the interest rate, which is 5%. And because it's 1 year, so we just do the compounding by once. And usually, if it's multiple years, then we will raise it to the power of t, right? So in this case, we only have like 100 times 1.75 because it's 5%, and then this is our the future value of our money if we save in the bank for 1 year, for example. So this is actually the formula which calculates the future value after with the annually compounded interest rate. So now let's switch to for example, the quarterly compounding or other compounding periods. Then let's draw some graph to better understand. So say this is t equals 0, t equals to 1, equals to 2. So just what happens is that we just directly jump from here to here, right? So this is annual compounding. However, if we were to compound, for example, 4 times a year, like which is called the quarterly compounding, then we have 4 compounding exercises, and then each of them will need to apply the same sort of rule to get the future value of the money. Now, each of them, the interest rate is actually calculated as, so say if I have m compounding periods in 1 year, so this is the number of periods, say m equals to 4 in this case. So I have 4 periods. Then this actually, the interest should be r divided by m. So this is the interest rate I would apply when I do the compounding at this specific period. So this is, of course, this period is 1 plus r divided by m. And because I need to do this multiple times, so that ends up being I need to raise to the power of m times t, because now I need to do this multiple times. So that's actually what happens if you have multiple compounding periods. So if we denote the future value of the money as A, then we can have this formula, which is that A equals to P times 1 plus. Now still our interest rate for each period, right, divided by M. And also we raise it to the power of I times T, because we still do this T number of years, right? And also each year we need to do this many times. So we times M. So another way to understand is that we still have P, and we need to do this for 1 year. We need to do this many times, and this is still this 1 year, and then we do the compounding, and also we reach the power of T, right? So T is the number of years, and that's actually equivalent, because based on our rule just now, this is how we would re-express the exponential function, right? So this is just some application of the exponential function. So now let's look at the one exercise. So here I've say I have $1,000 invested in the accounts, and it pays 10%, and also it compounded monthly, right? Monthly. So let's extract the information. So P is equal to 1,000 in this case, and this is annual interest rate, which is 10%, and we are compounding 12 times a year because it's annually. Now, what happens if it's after 10 years, right? So we just simply plug in. So it will be equal to 1,000 times 1 plus 10%, which is 0.1 divided by 12 raised to the power of 12 times 10. Right, so we can do the simple calculation, and we can use a calculator. So this is basically how we calculate the future value of the money, and it's one typical application of the exponential functions. Okay, so now if things gets more so what if the compounding frequency gets higher and higher, and we reach the so-called continuous compound interest? So continuous meaning that we actually decrease. So actually, for each compounding period, we actually squeeze it so that it's very infinitely small, and it becomes sort of continuously compounded, and the interest rate is actually reinvested in the same account to grow more interest. So that's the underlying working mechanism, and we would like to know how do we get the formula, and that formula is here. Right, so this is a formula to calculate the future value of money, and naturally you'll be wondering, how does this Euler's number, which we talked about briefly earlier, comes into play? Right, so remember, Euler's number is defined as the results of 1 of x to the power of x. So this is the expression as x goes to infinity. Right, so this is what happens. Now we have this form, which is original form of the discrete compound interest rates, so-called. So this is discrete because we have the limited number of times. So we want to sort of express this expression in a way similar to this one. Right, so that's because if we can do this, then we actually can bring in the value of E. So now we know that M will go to infinity, right? Because now our compounding period becomes smaller and smaller, and we have actually compounding more and more. So one way we can do this is to bring R to inside the parentheses, bring R to the denominator, right? So this becomes M over R, right? So we are getting somewhere. Well, this portion is becoming larger and larger. So R is still a fixed number because of its given interest rate from the bank, and T is also a fixed number. So the only changing part is M here. So so the denominator part is fine. Now let's look at this part. So this part, what do you do? We need to bring in, remember there's additional r here, right? So we need to bring sort of r in the exponents. Now, let's write down this portion as usual. And we need to maintain the same. So this is sort of our x here, which means that I will want x to be m over r. And let's put the m over r here, right? So to the exponent. However, we are short of the r itself, so we need to time r time t, so that r itself can cancel each other. So that's just to create additional r in the expression itself. So now we have this portion, and let me just re-express it so that it's more explicit. M over r and m over r also now RT. So we sort of use the rule of for the exponential functions, and then this is to raise into another exponent. Now, so this actually becomes very familiar to us because it's exactly following this format, right? So that's why we can bring the value of e. So so as m goes to infinity, now a would become p, and this is our Euler's number, which is our base. So our base is e, right? And times to the power of rt. So this is how we get the formula for the continuously compounded interest rate. Right, so just keep this in mind. If having expression, we will encounter this in the latest lectures. Right, so now next portion would be the logarithmic functions. So logarithmic function is the exact sort of inverse of exponential functions. So we can express it in this way: y equals to log b of x. So b is sort of our base, similar to the exponential function, and it's sort of equivalent. Exponential form would be x equals to b to the power of y. Right, so these two are sort of equivalent, and we're just bringing b from one form of is the same expression from one form to another by taking the inverse. Let's just look at a few examples. So we can do the conversion between logarithmic and exponential just by using the simple rules. So for example, log of 525 will be equal to 2, right? So this will be equal to 2. And this is sort of equivalent to 25 equals to 5 to the power of 2, right? So this is just common sense. Let's do another one. Log of 9, 3 equals to 1 over 2. So as I write the expression, you can sort of have a manual answer in your head to see what should be the number, and then it was sort of like, so you know how it's calculated. So by just moving moving the line to the, let's do like this. So 3 should be equal to 9 take 1 to the power of 1 over 2. So we basically do the square root, right? We're doing the square root of 9, and then to get the number 3. So it takes some time to adjust to this writing style, but essentially we are looking at logarithmic function, which will facilitate our expressions in many ways in the later analysis. So we can also do the conversion from exponential. For example, 46 equals to 2, 4 to the power of 3, or 3 to the 4 cube, right? So we can convert it to logarithmic, which is log 4. Now 4 is still our base, and 64, right? So we're taking the y to x, which is equal to 3. Right, so this is the sort of inverse conversion. And similarly, if 6 equal to this just common calculation, 36, now we can say log of 36, and this is actually equal to, can be expressed as this, right? So 6 equal to 1 over 2. Right, so let's just do 2 more. So if say we have the y equals to log 4 of 16. Now, how to get the value of y? If you are still not very used to the logarithm function, then you can say I can do something like this. So I can say 16 should be equal to 4 to the power of y, and that case me y equals to 2, right? So similarly, if log of the base of 2, x equals to -3, then I can express it as 2 x equals to 2 to the power of -3, and which gives me 1/8. Right, so this is just some way to re-express the same thing in different ways. Okay, so now when it comes to the logarithmic functions, there are two important things to know. One is the change of base formula. So what I mean is that if we say log of b and x, so and let me put a parenthesis here to sort of separate it. Now this can actually be expressed as log of c x, and it's actually divided by log of c b, right? Parentheses actually the same thing as log of cx, log of cb, right? So what we're doing is essentially we sort of insert another base, which is the new base c, and this is how can sort of expand it in this way. So this is the change of basis base here. If you want to change the base, there's another one more useful formula, which is regarding the Euler's number. So if x, so e to the power of x ln b here. So the particular ln is actually shorthand for log to the using the base of e. So this is just shorthand, and this can be expressed as b x here. So and then this is also because let me do a sort of derivation here. So e to the power of ln x should be equal to x, right? So this is the rule for using the exponential functions, and also with the exponent being the logarithm. So this is just one of the rules, and then we can so this guy can be decomposed as e of ln b, right, to the power of x. Right. So now e sort of cancels each other. Now we leave b inside, and then we have bx. So this is just the straightforward calculation. And also we can express the log of 2, 8 equals to 2. We can change the base to anything we want, so log of 10. So if, the upper we have the 8, and then below we have the 2. So let me just write it here. So for the top we have 8, for the bottom we have 2. Right, so this is just one way to express the same thing, and we can use another base, so which is base e, 8 log e 2, right? So because now we actually this also equals to 2 ln 8 and ln b. So this is how we often write the log with base e, with ln. This also is equals to log. And this is just useful things to know, because now log is also called the common logarithm, and this also called the natural logarithm. So we use when we say natural logarithm, we're referring to log. When we say the common logarithm, we're referring to log with a base of 10. Right. One more thing is that for the directionality of the travel, so if we have the function y equals to log b of x, right? So if b is bigger than 1, then the function is monotonically increasing, right? It's always increasing. And b, if it's bigger than 0, less than 1. So one thing we should note that b here is actually also the constant, the base. That's and also we need to satisfy condition b is bigger than 0 and b is not equal to 1. So the same condition as before. So now we can just draw some graph here to illustrate. So if b is bigger than 1, so this is the case where b is bigger than 1. So this is a function of the logarithm. This is how it looks like. And if it's this case, then in this case, then we can say it's drawn like this. So b is less than 1. Of course, it's bigger than 0. Right, so this is just regarding the directionality of the travel. Of course, we have the same point here. So if, say, x is equal to 1, then so log b1 should be 0, right? Because in this y equals 0. Now, this is also because b to the power of 0 is equal to 1, right? So this is the common points every logarithmic function would pass through. Right, so I think that's all for today's. Okay, so some more about the properties of the logarithmic functions. Let me see. Show the slides. Okay, give me a minute. Okay, so some properties of logarithmic functions. So one is the log base of b, y is equal to 0. And this is something we talked about earlier. And then if we take the x equals to b, then it will be 1, because b itself is actually b to the power of 1 is actually itself. So one more. So if we have b to the power of x, then it would be x in this case. Sort of these two terms cancel each out. That also means that it's equal to x times log of b, and then equals to x, right, times 1. Right, so same thing. We also have b to the power of log bx, and that's also equals to x, right? And in this case, we need to have x above 0. Some more. So we have log b of m times n. We can decompose this log bm plus log bn. Right. So this is converting the multiplication to a summation operation, which is actually very useful. And we have similarly, we have the division converted to a subtraction, right? Minus log of n here in this case. So one more, we have the log of b to the power, so we have the m to the power of p. So we can move p outside, p times log b of m, which is same thing as this one. So lastly, we have log bm, log of bn. They are equal to each other if and only if m is equal to n. Right. So this is some general properties for logarithmic function. All right. So that's it for this lecture, and thanks for watching. I look forward to seeing you in the next lecture.